Hey, what's up guys? Welcome back to your own YouTube channel. This is Shubh Gajjar from NIT-Surat. Today we are going to tackle the hard listed problem from Leetcode called trapping water. We are going to make it super easy to understand with visualized solution. So let's conquer this challenge together. Alright, let's take a closer look at the problem statement we are dealing with. We are given a set of bars where each bar has the certain height and each bar has the width of 1 unit. Our task is to determine how much amount of water that can be trapped between these bars if rain is pouring down. If this is the scenario, then we can say that the total number of blue units are our answer. Let's create a rough algorithm that takes big of n time complexity to solve the problem efficiently. We will traverse the height array from left to right and keep track of max height encountered so far. Let's see how the algorithm works. Initialize the two variables, max height that stores the maximum height encountered so far and trapped water to keep track of trapped water, both initially set to 0. Traverse the height array from left to right, starting from the first element. For each element in the array, compare it with current max height. Rule number 1. If the current element's height is greater than the max height, update the max height with the current element's height. If the current element's height is less than or equal to the max height, calculate the height difference between the max height and the current height. Add the height difference to the trapped water variable. Continue traversing the array and see the rule number 1 and rule number 2 for each element. Once we reach the end of the array, the trapped water variable will contain the total amount of water trapped between the bars. Let's try to solve the given problem using the given rules. Currently, we are at the index 0. At index 0, current height is 1, which is greater than the maximum height, which is 0. So according to rule number 1, we will update the maximum height with the current height and increment the pointer. Now we are at the index number 1. At index 1, current height is 0, which is less than the maximum height. So according to rule number 2, we will add the height difference between the maximum height and the current height to the trapped water and increment the pointer. Now we are at the index number 2. At index number 2, current height is 3, which is greater than the maximum height. Hence, we will update the maximum height with the current height according to rule number 1 and increment the pointer. Now we are at the index number 3. And index number 3, current height is 2, which is less than the maximum height. Hence, we will add the height difference between maximum height and the current height, which is equals to 1 to the trapped water, and increment the pointer. We are at the index number 4. At index 4, current height is 1, which is lesser than the maximum height, which is 3. Hence, according to rule number 2, we will add the height difference between the left maximum and the current height, which is 2, to the trapped water and increment the pointer. Now we are at the last index. At last index, current height is 3, which is equal to the maximum height. Hence, according to rule number 2, we will add the height difference between the maximum height and the current height to the trapped water. So here the difference is being 0, hence we will do nothing. Super easy solution, right? But will it be true for all scenarios? Let's see. I am appending the extra 1 block to the given height array. Till the index number 5, all performed computation will be remain same. Now let's see for index number 6. At index 6, current height is 2, which is less than the max height, which is 3. Hence, according to rule number 2, we will add the height difference between max height and the current height, which is coming 1, to the trap water. But stop, will it trap the water? There isn't any block on right side, hence not possible to trap the water. So we need to make some changes in our algorithm. If we are following rule number 2, then we need to ensure that there is at least one bar whose height is greater than or equal to the max height. In order to solve that problem, one solution can be to go right side before following rule number 2 and check whether there is at least one bar whose height is greater than or equal to the max height or not. However, this approach would result in a time complexity of big of n square instead of big of n, which is not desirable. Fortunately, we have a better approach called the two-pointer approach. This approach allows us to ensure the rules while maintaining an big of n time complexity for our algorithm. In this approach, we will initialize left pointer with the starting index of the array and the right pointer with the ending index of the array. We will move the left pointer and perform the same steps as in the previous approach, but instead of using the max height, we will use the left max. Similarly, we will perform the same steps with the right pointer, but this time we will use the right max. Now the question arises, when should we move the left pointer and when should we move the right pointer? And how do we ensure that there is at least one bar with a greater height on the right side? If the current height at the left pointer is less than the current height at the right pointer, we can confident that on the right side there exists at least one bar whose height is greater than or equal to the left max height. This indicates that water can be trapped and we can follow rule number 2. In this case, we will move the left pointer. On the other hand, if the current height at the left pointer is greater than the current height at the right pointer, then we are confident that there exists at least one bar with a greater height on the left hand side. Therefore, we will move the right pointer to explore the further possibilities. So now, when the left pointer is being greater than or equals to the right pointer, then we can say that we have successfully calculated the trapped water and we will return the trapped water, and this would be our final answer. Hence, the above algorithm will satisfy all the scenarios and we successfully solved this problem. Thank you for joining us today. Don't forget to subscribe to our channel, hit the notification bell and share your favorite puzzle solving moments in the comment below. Until next time, keep coding and may your solution always flow as smoothly as rainwater.